Hey everyone! Today we're going to start our very last chapter in our physics unit, and after this chapter, we're going to be moving on to astronomy. This chapter is titled Work, Power, and Machines, and specifically in section 1, we're going to focus on defining what is work and what is power. So let's go ahead and get started. Let's start us off with what is work? Well, in science, work is defined as the product of force and distance, which means that I'm going to multiply the force of something times the distance that force can get an object to move. In other words, remember, force is the push or pull on an object. So if I push an object and I measure how far it goes, multiply those two values, and that will give me the amount of work that I have done. Notice that these two things are required in order for work to be done. So if you don't apply a force, you haven't done any work. Vice versa. If it doesn't move, then you haven't done any work. So when is work done? Or our key question here is asking, when does a force do work? Well, there's specific criteria that has to be met. The first has to do with the direction that force is being applied. In order for a force to do work, that force must be applied in the same direction that the object moves. And this is a very key point. If it does not act in the same direction the object moves, no force is going to become work. Also, please note, if there is no movement, then no work is done either. On the opposite end of that spectrum, any part of that force that is not in the same direction is not doing any work. So again, here is our key header, and it describes the criteria that we need. It requires motion, so it has to move, and it depends on the direction. So again, depends on direction. I'm going to give you 3 scenarios, and then I'm going to give you a real life example of each one of these scenarios so that you can kind of see them and get a visualization for them. The first scenario says if all of the force acts in the same direction as motion, all of that force is going to do work. And this is actually where we get the maximum amount of work out of something that we can. The best example I can give you is the one that's pictured in your book. Note that here we have a lady and she's pulling a suitcase. She's pulling directly to the right, no slants at all. Note that the suitcase is moving to the right as well. Notice these 2 arrows are in the same direction, which means all of my force is going to be doing work on that suitcase. The second scenario states if part of the applied force acts in the direction of motion, then only that part is going to do the work. Let's go back to our suitcase example. Note here that instead of sliding the suitcase across the ground, she's carrying it, or in other words, rolling it at a slant. The suitcase's direction of motion is still to the right, but notice her force is different. Not only is she pulling to the right, but she is also pulling up. This vertical force right here is not in the same direction as my motion of my suitcase. Notice the arrows are going different ways. That means this vertical force is not producing any work whatsoever. The horizontal force, though, is in the same direction and therefore is doing work. And the last one says if none of the force is in the direction of motion, then you have done absolutely no work on that object. And the best example I can give you of this is when we carry things. If we go back to our suitcase example, She is pulling up or lifting up the suitcase. So the force is being applied in the upward uh, direction. But notice if she's walking, the suitcase is still going to the right. These arrows are not going in the same direction, so technically none of her force is applying work on this suitcase. Another way you could look at it is a person with a dumbbell. Here we have a weightlifter, and if I were to ask you, when is work being done and when is work not being done? First, let's talk about when is work being done. Well, we need motion and the force has to be in the same direction. Therefore, work is being done when the weightlifter lifts up the barbell with an upward force above his head. So going from the ground to above his head, that is when work is being done. There's motion, it's being pulled up, and it's moving up. However, once the weightlifter gets that barbell above his head and he's just holding it there, even though he's still applying a force, there's no work being done because that barbell's not moving above his head. It's staying still. With that being said, let's jump right into the work equation. Remember, work is going to be equal to the force times the distance. We need the force, and this has to be in the same direction as motion, and it has to have a distance. That means it has to move. Now that we've seen the equation, let's go over a couple of units that we need. In the last several units about motion, we've learned that force is measured in newtons. Remember, this is a capital J. Distance is measured in meters, which is just given a lowercase m. With that being said, the new unit that we're going to learn is the joule, which is given with a capital J. 1 joule actually equals 1 Newton times meter. And that makes sense because you're taking force times distance. So here's an example where we can use the work formula. Work equals force times distance. I'm going to go ahead and put my variables down here on the side and then see what we have. A weightlifter raises 1,600 Newton barbell to a height of 2 meters, and I want to calculate the work done to raise the barbell. Here, my distance is going to be 2 meters, and my force is 1,600 newtons. And right here, W is going to equal X. We can just plug and chug these into our equation. X equals 1,600 times 2. When you multiply those, you should get 3,200, and then you're just left with finding a unit. We calculated work, so our unit is going to be joules. Now to talk about the second half of this PowerPoint. What is power? Power is the rate of doing work. So that's why we had to talk about work first. Now, when we mention rate, usually that has to do with a time. How fast do you do things? In the case of power, how fast are you completing the amount of work that you're given? Knowing that, we're going to relate power, work, and time. So doing work at a faster rate is going to require more power. So there are 2 ways to increase your power. And I went ahead and started these in your notes. The first way that you can increase power is to increase the amount of work that you get done in a given amount of time. So say I gave 2 people 30 minutes to pick up as much trash as they could. The person who picks up the most technically has the most power because they did more work in the hour that I gave them. The other way is you can do a given amount of work in less time. So say I gave you both equal size yards. And I said whoever gets the trash picked up fastest is going to have more power. The best example that the book gives, and I like this example quite a bit, is talking about shoveling snow versus snow blowing snow, especially with all the snow that we've had this winter. Work is actually required to move snow from one location to the other because we're covering a distance and we're applying a force. A person shoveling snow with a shovel or a person using a snowblower can both do the work of moving the snow. However, when it comes to power, one is obviously more powerful than the other. And you guys can probably agree, and that is the snowblower. The reason is because it can actually remove the same amount of snow much faster. If I gave two people an equal sized driveway to clear out, generally the person with the snowblower will get done in the quickest amount of time. And that is because the snowblower has more power. Another way you could look at it is that the snowblower has more power because it can remove more snow for a given amount of time. So if two people were shoveling for a half hour, generally the person who has the snowblower is going to have more of their driveway cleared off than a person just shoveling. And hopefully based on these pictures, that man's going over to help that lady shovel her steps and driveway. That brings into our equation power equals work divided by time. And we like to say how things are related. So I'm going to talk about two things. First, if work increases, generally your power is also going to increase. And we talked about this being a direct relationship. On the other hand, if you decrease the amount of time you spend doing something, power will also increase. And we learned that power in time is going to be an inverse relationship. With that being said, let's go over units. Work is measured in joules, like we talked about a few minutes ago. Time is measured in seconds. And our newest unit, which is the unit for power, is watt. And this is actually equal to 1 joule per second. Hence, note that we're taking work divided by our unit for time. If you ever go to the grocery store, you might see a light bulb that says 60 watts, and that's telling you how much power that light bulb has. So let's go about calculating power. You exert a vertical force of 72 newtons to lift a box to a height of 1 meter in a time of 2 seconds. How much power is used to lift the box? First thing I always do is list what I have. So one of the things that I have is force. It says force is going to be 72 newtons. It also tells me that I have a height, which is a distance. That is 1 meter. And then it gives me a time. Time is going to be 2 seconds. And I want to know how much power do I have. If you think back, your power equation was work divided by time. If I look to see what I have time, but I don't have work. So I'm not sure what work is. Fortunately, we learned another equation to tell us how to find work. Remember, work equals force times distance. So you can see, do I have those variables to solve? And you'll see right here, I have a force and a distance. So work will equal 72 newtons times 1 meter. And this will give me a 72 joules of work. So now that I know work is 72 joules, I have enough to solve for power. Power is going to be equal to work, which is the 72 joules we found, divided by the time, which was 2 seconds. And when you guys do 72 divided by 2, you should get 36. Don't forget your units. We're using power, so it's 36 watts. This problem is solved much in the same way. You have to realize what you're given and what you're trying to find. Notice that here it's giving me a distance of 1 meter. It's giving me a force of 15 newtons. It's giving me a time of 2 seconds. I do not know my power, and I also don't know my work. So just like the last one, I have to solve for work first. Remember, work equals force times distance, or 1 times 15, which gets me 15 joules. I can then plug this into the power equation. 15 joules divided by 2 seconds gets me 7.5. And here I have power, which is going to be given in watts. Now to round it out, often units used in science are named after scientists who contributed a lot to the discovery or the usage of such units. For example, power is given the unit watt and is named after the scientist James Watt. Now, the watt isn't the only unit for power. Horsepower is actually another common unit, which is abbreviated HP. It is equal to about 746 watts. Now, why horsepower? Well, if you go out and you look at cars or you look at motorcycles, you can see that this has 100 horsepower or 250 horsepower. The reason that's a common measurement is because James Watt, the person who came up with the unit for power, was looking for a way to compare the power outputs of the steam engines he designed, and he compared them to horses. Why horses? Well, they were the logical choice to compare them with in the 1700s, and that's because horses were the main source of power. They pulled wagons, they were pulling plows. If they were building anything over mountains, they were the ones that carried all the supplies. So horses were very powerful. And this ends up on this picture, and it says the horse-drawn plow and gasoline-powered engine are capable of doing the work of a rate of 4 horsepower. And while I do like this image, I absolutely don't like it at the same time. It gives the common misconception that 1 horsepower equals the power of 1 horse, because here you see 4 horses and 4 horsepower, but that's not true. This does not equal. Horses can actually pull with a max strength of about 14 horsepower, so you have to be careful how you define it. Horsepower is given to the general amount of power a horse has sustained over an extended period of time, not in one instant. So please don't get that confused when you guys are learning this. And that's the end of my lesson today. If you have any questions, please make sure that you just ask, and I hope you guys have a great day.